everyone, and welcome to this lecture. When we studied discrete random variables, we've seen that the notion of expected value of a random variable or expected value of a function of a random variable gives useful information about the distribution. So, for instance, the mean value is sort of like the central measure. What is the, usually the random variable takes values around the mean. Usually, of course, it's important to know the variance also. And then there's the variance, which gives you a measure of the spread, okay, around the mean, right? So there's mean, which is sort of like the central value of the distribution. Let's put it that way. And then variance, which gives you the spread around the central value. So quite often it turns out you may not be able to measure or know the distribution of a random variable. In many situations, you'll only have data of sampled from what you think is a distribution, and in quite often the data won't be rich enough for you to learn the entire distribution. It may not be that much, and it may not be that spread out, etc. On the other hand, usually expected values, you can make very good measurements of. Even with limited data, you can get something reasonable about the expected value and variance and things like that. So to an extent, what you can learn about when you observe a random phenomenon, expected value is very useful. So in theory, how it plays with the random variables distribution and probabilities is important to know. We've studied it in the discrete context. We will extend it to the continuous context. Okay, so there's a very small adjustment you have to make to extend it to the continuous context, and we will do that in this lecture. Okay, so here's the definition theorem. I'm stating it as a theorem. One can actually define it from different way and prove it, etc. We won't do that. We will state it as a result and simply use it. Okay, here is the main result. Okay, you have a continuous random variable with a certain density. Okay, so it has a density also. It's small f(x) of x, our usual notation. And let's say g is some function. Okay, from real number to real number, it could be any function, any reasonable function, of course. Okay, so I've not been very precise about what that reasonable is, but just think of anything you can draw or anything you can describe in a reasonable way. Okay, the expected value of g of x, we will use the same notation as before. Expected value of g of x, e of g of x, the same notation. It's given by an integration. And what is that integration? Integral from minus infinity to infinity. It says minus infinity to infinity. It's enough if you restrict it to the support of x, okay, because if the support is not there, the PDF, the density is 0, so it doesn't matter, you don't have to integrate there. So for convenience, I'm just leaving it out as minus infinity to infinity. G of x times the density dx. Okay, this is called the expected value of a function g of x. Okay, so this is the connection. This is the way from the density you go to the expected value. Okay, so like I mentioned, quite often you may not know the density, but you can still know the expected value from other means. Okay, so we'll look at those kind of things later. Okay, so this is a very useful definition, very useful connection. Many of you can go back to the discrete case and make a very simple analogy here. So here is the analogy. The important thing to think of: if x is discrete, it has a certain range and it has a PMF Px, then expected value of g of x is summation over the range g of x times the PMF. So you can see what is going on here. So this sort of plays the role of summation. It's enough if you restrict it to support of x. Okay, support of x is like the range, and this sort of plays the role of PMF. Okay, density times a length, right? So the probability density times a small length is the probability that x is around, the probability that capital X falls around small x, and so you sort of multiply it with gx and then sum over all the support, which becomes integration in the limit and all that. So this is how the discrete goes into the continuous, and summation gets replaced by integration. Okay, and PMF gets replaced by that small probability measure in that area, which is density times this small little length dx. Okay, so that's the way to intuitively sort of think about it. I'm not being precise here. There's a way to write these things down precisely, but this is good enough for most of us. And anyway, the integration, we're going to use tables, and we will do that. Okay, a quick warning: and depending on the support, if the support is very large and then the function, the density function and the g of x are in a certain way, this integral may diverge to plus infinity or minus infinity, or in some cases it may not even exist. Okay, so it may not be able to fix one number for this integration. It might happen. So all those are sort of corner cases for us. Maybe I will mention it in one or two chance. If I get a chance, I might do it, but it's not so critical for us. Most of the time we'll be concerned with expected values which are well defined and finite. Okay, so this is the definition. Hopefully we'll see some computations in your examples and assignments. You will compute some expected value. Even in this lecture, I'll compute some expected values given some densities, and you'll see it's just an integration exercise in some sense. Okay, so let's come specifically to some specific choices of the function g. In the previous case, we used a general function g, and we sent expected value for g of x is calculated in that fashion. Okay, now for a continuous random variable, two particular choices are of great interest. One is something that gives you the mean value, okay, the expected value of x itself, okay, when g of x equal to x. So this is the case where g of x becomes equal to x. Okay, so in that case you have expected value of x. This is also denoted as mu sub x, or if the only random variable you're dealing with is very clear in the context, you can simply say mu. Quite often it's taken as the mean. Okay, and since g of x is equal to x, so the definition is quite clear: integral over the support of the random variable x times fx of x. So I keep saying minus infinity to infinity, but remember it's enough if you integrate over those values of x where the density is non-zero, right? So support is enough. Okay, so mean is the average value, expected value of x. It is sort of like the central value of the distribution. Okay, so it gives you a good idea of where the distribution is around. Okay. The next important special case of the expected value is what's called the variance. The variance of x. In this case, you can see the choice of g of x here. G of x is x minus mu x whole squared. Okay, so and the definition goes out very cleanly: integral minus infinity to infinity x minus mu x whole square times the density. Once again, the integration is enough if it's over the support of the random variable. So variance is the measure of the spread, and you can do a simple manipulation here, use the property of the PDF and show this very interesting result, that variance of x is expected value of x squared minus the expected value of x the whole squared. Okay, so this is a very useful result. So quite often when you want to find mean and variance of a random variable, you will find mean and then you will find expected value of x squared. Okay, so you find both and then you subtract and you get the variance. Okay, so that's how you do it. Okay, so clearly, if somebody gives you an arbitrary, so one of the skills that you pick up in a basic statistics probability course is, given the precise PDF, what is the mean, what is the variance. Okay, so it is an integration exercise. It's important to get a hold of that, and I mean you should have that skill. It's a basic skill that you should pick up when you do when you learn probability and statistics, and we will see a couple of exercises along that direction. But what is the meaning of the mean and variance? Mean sort of represents the central value of the distribution, and variance tells you something about the spread. Okay, and if you remember, we saw some inequalities and we will talk about those as well. But mean and variance are very, very crucial. Quite often in complicated cases, you can pretty much only compute the mean of the random variable, and that is actually powerfully good enough in many cases. Okay, so we'll see those kind of examples later on. Here are examples. Okay, so we saw very common continuous distributions, right? So we saw three types of distributions: uniform distribution, exponential distribution, and the normal distribution. What is the mean and what are the mean and variances of these distributions? Okay, so this is the slide that tells you that. This is an integration exercise. I'm not going to go through the integration exercise for this particular case, but I will suggest that you try it, see if you get it. This is a good exercise. You can try it with a pen and paper, and you'll get a good hold of some of these things. Particularly for the uniform, you should be able to do it. It's not very hard to do the uniform case. Okay, so for the uniform distribution, AB, you know what the PDF is, right? It's just flat from A to B. Height is 1 by B minus A. It is flat. Okay, so the expected value, very interestingly, happens to be A plus B by 2. It's not very difficult to guess the expected value. It's the mean value, central thing, etc. The variance comes out to be this number, b minus a whole squared by 12. Okay, you can get that if you do the integration. I'll once again, like I said, this is an exercise. Okay, For the for the exponential distribution, you remember lambda e power minus lambda x for positive x, that's the density. Okay, the expected value of x, if you actually plug in the formula and evaluate the integral, you will get 1 by lambda, and variance will be 1 by lambda squared. Okay, so this is an interesting little result for the exponential distribution. Most people, once they see this for a while, they will mug this up. They will know these things by heart. Okay, so what is the mean of uniform distribution, variance of uniform distribution, mean of exponential, variance of exponential. In particular, the most important thing, like I said, the most important distribution in all of statistics easily is the Gaussian distribution, the normal distribution. It has two parameters, mu and sigma square, that we saw before. This has this complicated e power minus quadratic PDF. Not complicated actually, it's a very nice PDF. The mean of a normal distribution is actually equal to mu, and the variance of a normal distribution is actually equal to the sigma squared. Okay, so this is something really interesting. So what this gives you are these very interesting results, right? So if you look at the Gaussian, so what does it mean to say mean of x is mu? Okay, so integral minus infinity to infinity x times fx of x, what is that? 1 by sigma root 2 pi e power minus x minus mu squared by 2 sigma squared dx is actually equal to mu. Okay, so this is a useful identity in my opinion, because if you think about it, this is just it's a complicated looking integral. It's actually not too bad. One can evaluate this integral. This integral ends up being mu. It's actually not very hard to prove, but anyway, I mean you can give it a shot. If you think you can prove this, that's great. Okay, look at this other integral for variance, as I'll write it down slightly differently, minus infinity to infinity, or maybe the same way, x minus mu whole squared times 1 by sigma root 2 pi e power minus x minus mu whole squared by 2 sigma squared dx equals sigma squared. So notice this identity, this is slightly more difficult to prove than the previous one, but it's possible. You can write down some proof for this. So these are all slightly more involved integration, but hopefully you can do this. Okay, and many people, once you get used to it, you can mug up this integration as an identity, and this will help you in some integration exercises. But in this course, in this program, we don't bother too much about such integrations. It's not so critical. I'm just writing it down for you to realize that it's a little bit more complicated. We won't go into such integration exercises in this class. It's not the main point of this class, but you should remember these identities, okay, these forms for the distribution, and the fact that the expected value is mu, variance is sigma squared. This is very important to know and appreciate. Okay, so in modeling this comes up quite often, and we should know this. Okay, so supposing, for instance, I'll give you some simple ways in which you can test. Okay, supposing you're observing a random phenomenon and it looks, maybe it feels like an exponential random variable. Maybe you want to model that as an exponential random variable. One very quick way of checking is to find the expected value and find the variance. Later on we'll see some quick way of estimating the variance and mean of a random variable from observed samples. Okay, so you can do that. It turns out you can do that with pretty reasonable confidence. Okay, so once you can do that, and if it turns out that the variance is square of the expectation, then it's sort of like an added bonus proof for you, when this is probably close to exponential. So things like that are quite useful in practice. So it's good to know what the mean and variance are of distributions. Okay, but the actual integration might be a bit more complicated. Okay, so that's okay. So here is a picture which maybe conveys what we're thinking of here. Different uniform distributions. Okay, the uniform distribution is around half. Okay, different widths. Okay, so the black one is uniform distribution from 0 to 1. Okay, and you can see the height is 1, right? The blue one is the uniform distribution from, so this is uniform 0, 1. The blue blue one is uniform the height is a half, so it will go from 1 by 4 to 3 by 4. Okay. The green one is uniform. Its height is going up to 4, so this I think is half minus 1 by 8 and then half plus 1 by 8. Okay, that's what gives you a height of sort of 4, right? So you can do this calculation. This is just basically I'm trying to convey how the last one is uniform. Its height is going up to 10, it's around 0.5, so that will be 0.45, 0.55. Okay, so you can see how this is working out. I mean, as the width decreases, the height of the uniform distribution is increasing. All of them have the same mean. Mean is 0.5, and the variance is going to be very different. Okay, so the variance for the uniform 0, 1 is 1 by 12. As you keep reducing the width, the variance will fall down. So maybe I should write down what the mean is and variance is for. First thing, the mu is equal to half. The variance is b minus a whole squared by 12, so that is 1 by 12. For this distribution, if you want to write the mean and variance, you're going to get mean to be once again half. Okay, the mean is half. You can see that sort of the central value is half, and then the variance. Of course, you need to do a plus b by 2 to calculate the mean, and that also will turn out to be half. Then for sigma squared, you want to do b minus a whole squared by 12. Now b minus a is 0.1, 0.01 by 12. So you can see, as you go from a wide, shallow sort of distribution to a small peaky distribution, even though the mean is the same, the variance is sharply falling. Okay. Now, so you can also have the mean changing. Now, for a uniform distribution, if the mean is changing, then it means that the whole uniform distribution shifts to some other place. Instead of mean being 0.5, if the mean were to be 5, this whole distribution with the same variance, for instance, will just simply shift to 5, as you can imagine. Okay, so this is just a picture to show you how what variance means for the uniform distribution. Okay, let's do the same with exponential distribution. You vary the lambda, and then you will get a sense of the different PMF and their mean and all that. So from this picture, you can see that there is the black, which is this guy here. So this is exponential 1, okay, and it has a mean of 1 and then a variance of also 1. Okay, so this one, the green one, is exponential 2, right? It's how do I identify that? It's I've told you it's exponential distribution. How do you know the parameter lambda? Remember, exponential distribution is lambda e power minus lambda x. At x equal to 0, the value you get for the density is simply equal to 2. Okay, so this is once again the density. Okay, remember, density. This is the density. Okay. So this guy is exponential 2. So the mean will be 1 by 2, and the variance is 1 by 4. Okay. So you can sort of see where the mean and variance would be. For the black one, the mean is 1 and the variance is 1. For the green one, the mean has shifted to the left. Okay, so half, you can see it takes lower values with higher probability, and then the variance is sort of 1 by 4. You can look at the blue one. The blue one is exponential half, okay, and mean would be 2 and variance would be 4. Okay, so you can see that the blue one has sort of lowered and it's spread out, right? It takes larger values with higher probability, so the mean value has shifted to 2 and the variance has become 4. Okay, so variance is also larger. Okay, so it shows you the larger spread. Okay, so this hopefully gives you a feel for how exponential works as you vary lambda in terms of mean, variance, and density. Okay, so you can see the behavior is very different from the uniform. but you get a sense of how this is controlled. Okay. So the last picture I want to show you is for the normal distribution. I've fixed mean as 0 for all the 3, and then the sigma has been varied. You can sort of guess where this would be. So this has, so let's write it in just black. So this has got, the black one has got normal, I think that is 0, 1 if I'm not wrong, that's what it is. So mean is 0 and then variance is 1. Okay, so the green one, so this is mean 0 and variance is greater than 1. Okay, so you can see the variance has gone greater than 1. It's spread out more, it has come down below, so that's a larger variance with the same mean. And the blue one, you can sort of guess it's mean 0 again, and variance squared is less than 1. Okay, so the sigma squared variance is less than 1. So it's a peaking thing, and it comes closer together, it takes values around the mean most of the time. Okay, so this is how the different PDFs would look. Okay, so this kind of a shape is a good thing to keep in your mind, right? So when you think of a distribution, what is the shape of the density? Okay, so that sort of tells you the kind of values it takes. On top of that, the mean and variance will give you something, and quite often the shape of the density might be difficult to get. Okay, the random variable you're dealing with might be very complicated. So, but mean and variance is something that you can hope for getting. Okay. So that's, I think that's all we wanted to do about mean and variance. So we will do a couple of problems of evaluating mean and variance given a density. But before that, I want to mention something about Markov and Chebyshev inequality. So if you remember, we used this Markov and Chebyshev inequality to calculate probabilities, to calculate bounds on probabilities that the random variable will take a value far away from mean, right? Far away from mean by so many variances, then we got an upper bound. Okay. So this, I said, sort of tells you how the mean and variance affect the distribution itself. Okay, so you can get probability bounds using mean and variance. Okay, so the same bounds hold for continuous distributions. In fact, for any distribution which has a mean and variance, the bounds hold. Okay, so that's the point of this slide. I'm trying to say that the Markov and Chebyshev inequalities carry over to an arbitrary distribution also. Okay, as long as mean and variance exist for that random variable. Okay, so probability that, what is Markov? Markov is, first of all, it needs a random variable needs to have non-negative support for Markov, and probability that x is greater than c is less than or equal to expected value of x divided by c. Okay, so that's Markov inequality. It's useful to get bounds for probabilities. Now, if you have mean and variance, Chebyshev inequality comes in. Probability that absolute value of x minus mu is greater than or equal to k sigma. Sigma times k is less than or equal to 1 by k squared. Okay, so that is Chebyshev inequality. Both of these inequalities are useful for getting bounds on x deviating too much from the mean. Okay, and that is useful quite often to quantify. Okay, so this holds in general for any distribution, not just for discrete, which we saw before. Okay, so a few, just one slide on the mathematical aspects of it. So far, we've just introduced continuous random variables in a very convenient, simple way from CDF and going to generalization of CDF. We never spoke about the probability space underlying a continuous distribution. Okay, so in the discrete case, we were able to describe the sample space, which was the set of all outcomes, and then we were able to describe events as subsets of the sample space, and then unions of events, intersection of events, and then the random variable came as a function from the sample space to the real line, right? So that's how the random variables were defined. Okay, can you do something similar for the continuous case? Okay, so that's a question that one may ask. It turns out the technical nature of the answering that question is too complicated. And it's, let me not say complicated, it's just that it's the jargon and the language needed there is a bit more involved, and it's very technical. And I've skipped that totally here, even though your book has a description of that. I'll welcome you to read the book and see if you can follow the description. So I'll just briefly summarize it. This is only for those who are very heavily mathematically inclined and would like to know what it is that we missed when we did this simplification. Okay, so the sample space you can take as, for the continuous case at least, you can take it as the interval of a real line, for instance. Then events, will be intervals within that, their unions and complements. Okay, so this is how events are defined. It turns out you can't say all subsets. There are some bizarre subsets which are counterintuitive to our sense of measure and all that. So we don't do that. And the probability function can also be reasonably defined. Okay, so all of this can be done. A proper probability space can be defined for the continuous random variable also, and you can define the continuous random variable as a function from the sample space to the real line, and then work with that and all that. All that's possible. Okay, so in fact, the modern theory, modern probability theory, does not necessarily need to distinguish between discrete, continuous, mixture and all that. There is a uniform language in which all of these can be described in common. That is the language of measure theory, and that is way beyond the scope of this introductory course. I'm just putting it out here so that in case you're interested in studying more about the theoretical aspects, you can look up NPTEL courses of that I've pointed out here. It gives a complete characterization of the measure theoretic description of probability. It's an advanced course. If you're thinking of graduate studies and all that, you can jump into it. Okay, so this slide is just a small bow at the axiomatic nature of probability theory, and something that we've skipped totally, but still it's good to just know that these things exist. Okay, so let's come to a couple of problems. Like I said, a very important skill that you need to pick up is, given a PDF, right, evaluate, say it's CDF, expected value variance. Okay, so it's something, a very basic skill in continuous random variables, and since this is one of the first courses you're doing, you should pick up that skill. You should do some problems, enough problems to be comfortable with going from PDF to CDF and finding the expected value and the variance. Okay, so many of these are exercises in integration, so this will also help you, looking at a table of integration and then making sure you can go from the table to substituting the value. We won't expect, at least in this course, we are not going to expect major wizardry in the integration itself. It's not a point of this course, but just the basic skill of what is involved should be known to everybody. Okay, so let's get started. So I'll work out a couple of problems. I have two problems that I picked out. Both are from the book. So this is just to get you some practice. Okay. So here's PDF, 1 minus mod x between -1 and +1. I usually like to sketch the PDF. You don't have to sketch if you don't want to. For some reason it became blue, so let me do black. If you can just imagine the formula without sketching, that's also good. You don't have to. So it's 1 minus mod x. It would look something like this. Okay. So it's a valid density. You can see the total area under the curve is half into 2 into 1. That's 1 itself. It's just the area of this triangle, isn't it? So that's the PDF. So you can see support is from -1 to 1. So immediately, if we have to do the CDF, two regions is very clear, right? It's going to be 0 for x less than -1, okay? And it's going to be 1 for x greater than 1. Okay, both these things are very clear. And it's very likely, given the nature of this PDF, you're going to get something here for -1 to 0. Okay, maybe I'll put the less than or equal to on one side, doesn't matter. And then from 0 to 1, okay, you're going to get something here, right? So this is how the CDF is going to look. How did I do this? I mean, so you see less than -1 is going to be 0 all the time, greater than 1 it's going to be 1 all the time, and then from -1 to 1 you'll have one type of integration, and then 0 to 1 you'll have the other type of integration. So what do I do for -1 to 1? So for x in the range -1 to 0, the CDF of x is going to be integral from -1 to x. If you want, you can write down the formula here. You'll have 1 minus mod u du. Okay, so I'm just doing it laboriously. There's so many other easy ways to do it. Integral -1 to x. Now remember, u is all negative here, so absolute value will be minus u, so it will be just 1 plus u du. Okay, is that all right? Hopefully you see where I got that from. So if you do this, you're going to get -1 to x. 1 is just u itself, right? So u evaluated between x and minus 1 plus another u, which is u squared by 2 evaluated between x and minus 1. So you get x minus minus 1 plus x squared by 2 minus minus 1 squared by 2. Okay, so you will get here x plus 1 plus x squared by 2 minus a half. So if you want to write it down in its entirety, half plus x squared by 2. Okay, so that's the formula for this. And then for the other range, 0 less than or equal to x less than or equal to 1, your fx of x is going to be, see, notice this is 0 to 1. So if you're going to integrate, you're going to do minus 1 to 0 of 1 minus mod u du plus 0 to x 1 minus mod u du. Okay. So this guy is simply something we evaluated before. This will come out to just half, right? This is like putting x equal to 0 here. I've just evaluated minus 1 to 0, so this is x equal to 0 here, and that's just putting x equal to 0. You will get a half. For this one, you have to repeat the calculation. So this is going to be half plus, so integral, this u is positive, so you'll get 1 minus u. So you'll have u evaluated between x and 0 minus u squared by 2 evaluated between x and 0. So this will be half plus x minus x squared by 2. Okay, so that's the formula. You can put this back in. So this would be half plus. You can go back and fill in the question marks here. Okay, you'll get the CDF. Okay, so like I said, this is not very hard per se, but if you've not done this before, if you've not done these integrations and carefully written down, tomorrow if I change this function, okay, instead of 1 minus mod x, if I give you some other function, you should be able to repeat this exercise. It's a simple, at least for simple functions like this. We won't give you very complicated functions, maybe steps, maybe simple things like this, but you should be able to split it and write out in different regions. It's a basic skill, and the basic skill is needed in a bachelor's program. Okay, so you need to pick this up. This is CDF. So what about expected value and variance? Looks like I might run out of room here, so let me see if I can simplify this a little bit. Okay, so for computing the expected value of x and variance of x, I'll do it sort of the laborious way, but if you look at this function is symmetric about 0, right? Whenever you have a symmetry about 0, the point about which it's symmetric will become the expected value. So in this case, ahead of time, I can sort of guess that the expected value will be 0. Okay, so maybe we can do this calculation also, but it will come out to be 0. It's not too difficult to check this. So let me see if I can do that for you. Okay, so expected value of x, if you have to just laboriously do it, is it's integral over the support x times fx of x dx. Okay, and since there are two different functional forms, you might want to do minus 1 to 0 x times 1 plus x dx, right? Remember, it's 1 minus absolute value of x. When x is negative, absolute value of x is minus x, so it becomes 1 plus x dx. Okay, think about why that is true. Then you have 0 to 1 x times, what is fx of x from 0 to 1? It's 1 minus mod x, and x is positive, so mod x is just x dx. Okay, so one needs to evaluate this, so let's just go ahead and evaluate it. It is just x and then x squared. It will be x squared by 2 between 0 and minus 1 plus x cubed by 3 between 0 and minus 1, and then again x squared by 2 between 1 and 0 minus x cubed by 3 between 1 and 0. Okay, so this would just be minus half, the first one. See, if you put in 0, you're going to get 0, minus of, just instead of x you put minus 1, so it's minus half. So here again it will be 0 plus 1 by 3. So here it will be plus half, and then here it will be minus 1 by 3, it's 0. So you can check that even if you use the formula and do it carefully, correctly, make sure you put this correct substitution, you're going to get the same answer. Okay. For variance, I like to, so in this case, expected value of x is 0, so variance of x is equal to expected value of x squared. So it's the same thing. Instead of x, I have to put x squared, right? So x squared times 1 plus x dx. I'm jumping straight into this step, right? I can simplify this step, x squared times 1 minus x dx. Then after that, I'm just doing the usual thing, x cubed by 3, 0 minus 1 plus x power 4 by 4, 0 minus 1 plus x cubed by 3, 1, 0 minus x power 4 by 4, 1, 0. There may be smarter ways to do this, but we should know the laborious, ugly way as well. 1 by 3, okay. Once again, minus 1 power 3 equals to 1 by 3 plus, in this case, it's actually again minus, I think, minus 1 by 4 plus 1 by 3 minus 1 by 4. I hope I got that right. Okay, I think that's correct. Okay, so it's 1 by 3 minus 1 by 4 plus 1 by 3 minus 1 by 4. 1 by 3 minus 1 by 4 is 1 by 12. 1 by 12 plus 1 by 12, that's 1 by 6. So the variance works out as 1 by 6. Hopefully I didn't make any mistakes here. So this is the expected value of x and variance. So you see, it's simple integration, knowing the formula. So the only formula for integral that we needed was integral x power n dx is x power n plus 1 by n plus 1. So this is the formula that we needed, and then splitting it up, and then so for absolute value of x, it's minus x if x is less than 0, and it's x if x is greater than or equal to 0. So we used simple things like this, and then we were able to reason it out. Okay, so that's the first example. Hopefully this was clean and you could follow. Okay, all right, so this is the next example. Okay, so this involves slightly more complicated functions, trigonometric functions, but I mean, there's no need to be too scared about trigonometric functions. Again, the tables for integration and all of that is available. Okay, so you might want to sketch this. So if you sketch fx of x minus pi by 2 to pi by 2. If you're really worried about trigonometric functions, I'm just showing this as one example. There's no need to worry too much about it. It's just a shape, and okay, I think my scale didn't work out okay for here. Let me just see what happens. Okay, it will have a shape like this. Okay, some such shape. Okay, so this value will be half. Okay, at this point, and this integral will turn out to be 1 and all that. It's quite standard. Okay, the CDF is once again, so it's easy to find. So looking at this, the support you see is between minus pi by 2 and pi by 2. CDF is going to be 0 for x less than minus pi by 2. It's going to be 1 for x greater than pi by 2. So between pi by 2 and pi by 2, what is it going to be? Okay, so I like to do this always. When I have to find the CDF from the PDF, first I like to write what I know clearly from the support itself, and then what I have to find from the integration, and different regions. If there are different function definitions, put question mark, write down the region clearly, and then go after each region and find the integral. Okay, so it's just the step-by-step method that you do. Okay, so here is the region I'm going to focus on, and then try and find fx of x. It's going to be integral minus pi by 2 to x, and then it's going to be fx of u du. Okay, notice how I'm changing these variables, right? So why did I do that? If you think about it, this x is already shown up here. No point in putting x inside here again. You'll get only confused by that. Put some other variable, and then the integration variable is clearly different from the variable you're using for the limit. Okay, so now we have to go to the formula and look at cos. It turns out the integral of cos x dx, if you go look at it, you'll find it's sin x. Okay, so this is a standard formula one can just use. So if you go look at half is just half. It's just it's going to come out, and then you just have integral sin x between x and minus pi by 2. Okay, so so this would work out as half sin x minus sine of minus pi by 2. It turns out sine of minus pi by 2 is actually minus 1. This is actually minus 1. So you can look this up. This will come from some formulae. So this is 1 plus sin x by 2. So that is the answer for the CDF. Okay, easy enough. I don't know. I mean, if you're uncomfortable looking up integral formulae and then plugging it back in, and you're worried about trigonometric functions, you don't feel comfortable with cos, sine, etc. I apologize. This is a very standard example in a book just to get you to practice the integration. You just go look up the table, plug it back in, and how do I know sine minus pi by 2 is minus 1? I mean, you can use the calculator. Calculator in radians will give you the sine. It's minus 1. You'll get 1 plus sine x by 2. Okay, so that's the CDF. Let's do expected value and variance. Before we even do expected value and variance, given the symmetry of this function, what is expected value of x going to be? It better be 0, right? So that will work out quite nicely in this case. Variance, you may have to do some slightly more complicated integration. So the type of integration that's needed, usually it's a bit worrying, because I mean this integration may not be a standard integration that you would have seen. Let me see if I can give you some clear values from the table. Okay, so let's continue. This is probably the only example you're going to ever see with integration and all that, and don't be too worried about integration, because any integral that you will actually need for a problem, we will give you. You only have to just pick up that integral and substitute it with the limits. We will not expect you to know the integral by heart, so don't be too worried about it. So for instance, in this formula, in this problem, you needed to know the integral of cos x, that's given to you. And going further, when you want to find mean and variance, you need two other integrals, integral of x cos x and integral of x squared cos x. All of this are given to you. Okay, so you'll have to just substitute formulae. Don't worry about the integration part. Okay, so given this, let's go ahead and do expected value of x. Okay, so this is going to be integral minus pi by 2 to pi by 2. That's the support of the density, x times the density itself. That's half cos x dx. Okay, so now x cos x is here, and for the integral x cos x, I've given you a formula. So you need cos x plus x sin x. Of course, there's a half outside, that's to no consequence, minus pi by 2 to pi by 2. Okay, so if you start substituting pi by 2 here, cos pi by 2 turns out is 0. You'll have a plus pi by 2 here, sin pi by 2 is 1. Okay, so you'll get something there. And then you put minus pi by 2, cos minus pi by 2 is also 0. And then you'll get a minus pi by 2 here. And then sine minus pi by 2 turns out is minus 1. So everything will work out, and finally you'll see you'll get a 0. Okay, so this needs checking. So maybe I should do this in some detail. Half of cos pi by 2 plus pi by 2 sine pi by 2 minus cos minus pi by 2 minus pi by 2 times sine minus pi by 2. Okay, so all this needs calculation. Cos pi by 2 is 0, cos minus pi by 2 is 0, sine pi by 2 is 1, sine minus pi by 2 is minus 1. Okay, so it's pi by 2 plus pi by 2 minus, everything will cancel, you'll get 0. Okay, so this is something you have to do. So plug in these formulae into your calculators, you will get it. Okay, so the integration will be given to you. You won't be expected to remember the integration, but you should be able to pull the integral from somewhere, plug it in, and get the answer. This is a skill, a basic bachelor's level skill for computing expected value. Okay, so given a PDF, given the formulae for integration from somewhere, you should just pick out and calculate the mean and variance. Okay, so for the variance, once again, the expected value is ending up being 0. So variance of x is the same as expected value of x squared. Okay, so that will be minus pi by 2 to pi by 2. Once again, the support of the density x squared times half cos x dx. Okay, so now this half is going to come out, and then you have this more complicated looking formulae, sin x plus 2x cos x. It's just mechanically doing it. There's no need to be alarmed or anything. Minus pi by 2 to pi by 2. You don't need any wizardry, like I said, in the integration. We won't expect that from you. But at least the substituting into the formula, that will be expected. Okay, so there's going to be a half outside overall, and then inside I'm going to plug in pi by 2. So it helps to know, for instance, you calculate the sine and cos separately. Cos pi by 2 will go off to 0, sine pi by 2 will end up being plus 1. So you'll just get pi by 2 squared, which is pi squared by 4 minus 2 here. That's what will happen if you put in pi by 2. Now when you put in minus pi by 2, you're going to have a minus overall, and then when you put in minus pi by 2, the sign will become minus 1. Okay, so you will get minus pi squared by 4, minus pi by 2 cos will go off to 0. So here again you'll have minus 2, so this will be plus 2. Okay, is that okay? So you see it's pi squared by 4 minus 2 minus pi squared by 4 plus 2. So this will work out as just half, and that will cancel. So you'll get pi squared by 4 minus 2. Okay. So you get an answer for the variance. It's not a very high value. Pi is some 3.14. 3.14 square is some 9 point something, by 4 is 2 point something, minus 2 it's 0 point something. So it's a small value, but that's the exact value of the variance in this case. Okay. So hopefully these two problems are illustrative, and you will get some more practice for problems like this. Once again, I want to remind you the integration will be given to you. You should just be able to identify the intervals and plug in the formulae there. Okay, so this is a basic skill that one should know when you deal with continuous random variables. Okay, so this sort of finishes most of what I wanted to do as basic skills and ideas in continuous random variables. What I also want to show you in the next lecture is how to simulate these continuous random variables in the Colab notebook. So we'll see that in the next lecture.